And okay, are you seeing just my title page, or are you seeing the part that has previews and stuff on it?
Just the title.
This title, okay. Just so I know. All right, so reminder, we'll have a test next Tuesday. Wish we could have a little bit more time in between, but grades are due on Thursday, so not much choice there. Homework 2 is due on the 3rd, and we'll spend a lot of time today going over that. Hopefully we'll have time to look at a little bit more about correlation and match filter receivers. So last week we introduced them kind of at a block diagram form, and I talked about them a little bit, and we'll just go a little bit deeper today. So the homework is homework. I don't know if y'all looked at that. Let me drag it up here onto this screen. And so they're all out of the book. If you've managed to find a copy of the book, then you can just refer there. But hopefully I have transcribed them accurately onto this assignment here. So we're gonna here just specify a grade code for the 16 Comm. Of course, we did this on the last exam. Just wanting to make sure that we really understand this. This is more involved. Now you got 16 of these guys, right? So but we'll talk a little bit about that. Then I wanted to reinforce some knowledge about FSKs, frequency shift keying modulations. They are an important part, and I picked this problem out of the textbook, but then when I was going through it and solving it, it's like this thing is non-trivial, and it's really covering a lot of material that we haven't covered in class and stuff. So I'll talk about it. So if you do want to go deeper in it, I'll talk about that today, but we're not going to, you don't have to do that one for your homework. So, but then there's a binary digital system. This is on-off keying. And so we've looked at binary antipodal signaling, where you have something that's plus and minus. That's really equivalent to binary phase shift keying, where the phase is 0 and pi, or 0 and 180 degrees. So it's really kind of the same, whether you negate the amplitude or you add in pi radians of phase into that cosine argument of a typical symbol shape, then you're achieving the same effect, right? And then we also looked at quadrature, both in the lecture and on the test. Quadrature binary signaling, where the binary indicates that there's two symbols, and the quadrature is describing the relationship between those two symbols. Here we've got a symbol at amplitude A, and also one that's amplitude 0, or basically we're not going to send anything, right? We're not really transmitting that. So and then finally there's this binary PSK, BPSK, and we'll work through this problem here. So come on. There we go. All right, so hopefully you see my slide again, homework 2, grade code. So I believe I mentioned this technique and may have even provided the link to an online resource to do it. But here I'm going to lay it out, one method to calculate grade codes for larger K. I like this method because it's pretty turnkey, right? You just plug and chug. But it's iterative, right? So you start with one with size L, let's say, that you know. And well, it's pretty easy. We've done it a number of times to do one with K is equal to 2. So it's 0, 0, 0, 1, 1, 1, and 1, 0, where now each of these steps from here to here to here and then back here, only one bit is changing between these steps, right? And but how do you scale that up to larger K? Well, here's the rule: concatenate a reversed copy of the previous set. So this is the previous set up here, and then reverse it and concatenate it, right? So now we'd have 1, 0, 1, 1, 0, 1, and 0, 0, right? And then for that first set, prefix that with a 0, and the second set with a 1. And you know, magically it works out. Make sure you check this last one because you got to wrap back around to the first one. But you'll see that in each of those cases, only one bit is changing. So in this in the homework case, you're going to need to go one more level, right? So this is K is equal to 3. It's going to give you 2 to the power of 3, or 8 different symbols, codes associated with the symbols. And for K is equal to 4, now it will, what we're implying is that we're grouping 4 bits together to form each symbol. So we're trying to assign those, you know, set of 4 bits to each symbol in such a way that we satisfy the gray code criteria. So the first step on this homework assignment then is going to be to calculate the gray code, first of all, and then assign it to these constellation points. Here, what is important is that you need to figure out what the nearest neighbor is, right? So for here to here, that's the nearest neighbor, right? And then to here, here to here, that's a nearest neighbor, that's a nearest neighbor. That's not, right? That's a longer distance. So yeah, so you might need to think about how you assign those things there. So all right, so the next one gets pretty involved, and one way of solving this is what we're asking is the power spectral density of an FSK, a binary FSK modulation system with random or discontinuous phase, right? So I think we briefly talked in lecture. We haven't done much more about it, but the idea of a continuous phase version of that, where we constrain the phase from one symbol to another to have continuous phase, even if the frequency is changing, right? And but we haven't done much more about it than just presented in lecture. This approach, the textbook goes through and derives a kind of a generic process for calculating the power spectral density of a memory-based system, and then notes that it simplifies when you don't have memory, when you only have one memory state. It's a Markov system, but if you're not looking way back in the past, you don't have that deep a memory, then it all gets simpler. But we kind of start off with the generic case to begin with. Recall that frequency and phase modulation, those are happening inside the cosine term, and so that kind of turns it into a nonlinear type of modulation. But so you would go through this process. This is all kind of defining this equation that the book derived, the textbook derived. And then we can simplify it because they're in this particular problem, k is equal to 2, and that should be P0 and P1 are equal to 1/2. In other words, they're equal probable symbols. And so you can start to simplify it where you note that these SO and SF would be the Fourier transform of this pulse from 0 to t. So it's a time bounded pulse that we'd be looking at. So like I say, I think it that could get you started, but it's still a little complex, and I'd rather not you burn a bunch of time with that. We only have so much time in this course, so let's focus on other things. The on-off keying, again, this is looking at this decision areas and probability of error. So we can one way of doing it would be to find a threshold. We can plot the constellation, use our graphical rule where we draw a line between the nearest symbols, and then we draw a perpendicular bisecting line with respect to that connecting line, and then that new line, the perpendicular bisecting line, becomes our decision boundary, right? And then we label our areas accordingly. So we could do that, and that's easy to do because the symbols are equal probable. If they're not, then you need to account for that bias term that we looked at earlier. So then you do need to figure out where the vectors are. So we can say that the received vector is this depends on a symbol that was sent, S0 or S1 plus noise, right? And S0 is 0, and S1 is this A times the square root of t. So this is where you're integrating. Here we're assuming that this pulse runs from 0 to t, right? And so when you kind of convert this into a vector, this is the amplitude you should end up with. Our noise variance we describe as n0/2, right? So basically then your next step is to plug that into your equation for a Gaussian PDF, right? It's that coefficient 1/square root of blah 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 2 pi sigma something sigma squared, and then times e to the power, and there you have the random variable minus the mean divided by the variance again, and all that's quantity squared, right? I'm doing it off the top of my head, so maybe that's right, or maybe it's just close. I don't know. So but plug that into the Gaussian PDF, and forming the probability R given S0 is transmitted, the probability of R given S1 is received, right? And so in one case, you're going to have a distribution of noise around 0, right? So if you draw out your constellation, then you're going to have this kind of Gaussian distribution around 0, and you're going to have a Gaussian distribution of noise around a root t, okay? And so that should kind of give you, an indication of how to write those Gaussian PDFs, how to plug these probabilities in, and and also how to solve them, right? So, but basically, if your probability here that you're calculating, this is how you would design your receiver, right, and your decision area. So if the probability that SO was sent, given SO was sent and R is received, is greater than the probability of R given that S1 was sent, then you decide for S0. You decide that, oh, I'm going to assume that S0 was sent, right? And we've talked about this, but conversely, if probability R given SO was sent is less than the probability of receiving that particular value of R given that S1 was sent, then you decide for S1, right? So this is basically setting up our decision boundary, right? So so I'll introduce a new notation here. It's communicating the same idea as this, but you may see this written down in textbooks and papers and that type of thing. So basically, you've got this relationship here, and if we divide now R S0 divided by R S1, and you'll see that, well, if your numerator is greater than your denominator, it's going to be greater than 1, right? And so that would satisfy this first statement. And so we would write this greater than 1 over here and an S0 up here. But if your denominator is greater than your numerator, then the result, this fraction, is going to be less than 1, right? So then you write, then that is satisfying this equation, the second equation, where we're mapping to S1. And so we write this as S1. So it's this little stack of greater than, less than, and 1. And we're writing these probabilities as a ratio. So now, as it turns out that both of these numerator and denominator will have the same base, right? So because what we're doing is we're plugging in this Gaussian PDF, right? So you're going to have this coefficient, and you're going to have e to this, relationship up there that is characteristic of the Gaussian PDF. And so since they're the same base, well, when you divide things with the same base, you can subtract the exponents, right? So we'll do that, and then you can kind of solve the algebra, expand those out. So your exponent should be in terms of R and this A times the square root of T, and your noise variance also. And so then you can just expand and simplify that they're in squared terms and stuff. So when you run through that, it'll simplify a little bit. So now that's part A. That will define the decision boundary, and you should get basically what we do with this graphical approach here. And but for part B, it's asking you what the average error is. So we know that the symbols are equiprobable, and so you're going to send you're going to have an average of the errors, right? So your overall probability of error is going to be basically the average of the probability errors when S0 is sent and the probability errors when S1 is sent. And so we integrate the Gaussian PDF for each symbol, setting the integration limits for the error condition. Right? So this is essentially changing it to a distribution function from a PDF, but what we're looking at is the area under the curve, or the tail of that Gaussian PDF, when it's in the wrong area, right? So remember, an area is when an error occurs when we calculate this probability for, our given R, our received R, given this S0, and because there's so much noise, that our received R ends up lying in the other decision area, right? So in the S1 decision area, in this case, but S0 was really sent. That would be an error. And the receiver, all it can do is examine R and know some assumptions about the transmission system, that it's equal probable, and what the symbols are. But at the when it's running, all it can do is observe R. And if there's so much noise and R lands in decision area 1, in spite of the fact that symbol 0 was sent, then the receiver is going to make an error. And conversely, if the receive vector lies in decision area 0, but actually symbol 1 was sent, then it's likewise going to be an error. So we want to calculate those rates. And so the thing that's going to make that happen is the Gaussian noise. And that's going to, you recall a Gaussian is this bell curve, but those tails go on forever, right? So the tail will cross that decision boundary. And when it does, that represents that probability of error. So you're going to integrate that area under the curve, under that tail. And so that's going to give you the familiar Q function type of thing. The key here is setting up the integration limits. So pay attention to that. So okay. All right. And then so the last problem is looking at the BPSK, binary phase shift keying, and we're interested in what amplitude do we need to achieve a certain error rate or better, but an error rate at a certain rate of transmission, right? So a lot of what we've talked about has kind of been ignoring rate and pulse durations and that type of thing. So we're now starting to look at some of these issues, right? So because we don't just send one symbol, we send many symbols, and one right after another. So so use the Q function, study the argument, right? Note that BPSK is the same constellation as binary antipodal pulse amplitude modulation. But instead of negating A, we're adding pi to the phase. So you're going to get the same results. There's a little bit more degrees of freedom with binary phase shift keying, in that it could be like plus J and minus J radians, or pi over 2, plus or minus pi over 2 radians, but usually we're that absolute phase is irrelevant, and so we just call it 0 and pi. So it really looks the same. So go back and pull out what we derived from lecture 7. I think slide 18 is like the last slide in that lecture or something. But then you'll see that probably an error in terms of the Q function is this square root of 2 times the energy per bit divided by the noise, and 0. Recall that we can say that the symbol energy is the same as a bit energy because these are binary type systems, right? So so now we can see that the energy per bit is provided in terms of A and T in the problem. And so use the Q tables, but now you're working backwards. So you're going to enter it. I think it's asking you for 10 to the minus 6 error rate. And so you enter the table there and get the argument that corresponds to that that error rate, the argument of Q. So we're kind of working backwards from the way we've worked before, and then solve for T, basically, where T is your period, and understand the difference between period and rate, right? That's just a reciprocal relationship. Okay, so that's hopefully gets you a good start on the homework. And so now I want to talk a little bit more. Let's see, I'm actually going to pull up our last week's lecture here to review. Okay, so we talked about correlation receivers. We noted that, yeah, we derived this concept of this map receiver and how it involves Bayes' theorem and conditional probabilities, and we're kind of flipping those conditionals using Bayes' theorem and stuff. But noted that the receiver is really seeing signals, not vectors. All that work is using vectors, but so we really need to convert these signals that the receiver is getting into these vectors and stuff. So when we look at this, this maybe could be written in a little bit more digital communications way, in that these RFTs and these are basis functions. These are symbols and or design symbols of our constellation, and these are the bias terms, right? And then at the end here, we threshold and select the largest. But when we draw this, we're really not, tracking time in the way we really will, right? So this signal coming in here, writing the way we are, we should recognize that this is really like an NT type of series of samples coming in, right? So this is a digital communication system, and at some point there's an A to D converter up front, and it is converting things into samples. But then we are going to then have another sampling where we, in this block here, we look at a result at a certain time and make our decision. Right? So you could, in the old days, this was implemented in analog systems, analog circuitry. So it's not wrong to have these T's here, kind of implying that this is continuous analog type signals, but in a more modern type configuration, you're most likely doing all this in digital signal processing. So all right, so we have that correlation receiver. Then we have this simplified version. We didn't talk a lot about that jump, how you can simplify it. The book talks about it a little bit, but even it doesn't really go into a lot of depth. But then we also talked about this matched filter receiver, and I kind of put this little hand wavy statement here: the filter shape matches the spectrum of the symbols sent, right? So But here we're starting to look at, so we're going to convolve. That's what a filter does in a time domain, right? We'd have an RFT coming in here, and we're going to convolve that with the impulse response of this filter. And then we're going to sample it at some time and look at the amplitude at that moment of sampling and make a decision. Is that S0 or S1 or S18 or whatever, however many symbols we have, right? So we're going to examine it. We're going to try to figure out what decision area it's in by comparing it to the decision area boundaries, right? So so in mathematics, when we're working with this, we often find it easier to calculate the Fourier transform of your signal and of your filter, and then we can just multiply the signals with the spectral response of the filter, and then we have the response of the Fourier transform of the output of the filter, right? We can just multiply that frequency by frequency. And in fact, if we convert to dB, because of the logarithm, now we're adding. So it becomes an intuitive approach, right? By working with h of f and by visualizing our input and our output signals in the frequency domain and stuff. So that's oftentimes how we look at things. And so we'll see a signal might have a certain shape, and the filter might push down, some things out of band, and preserve things in band of that filter. But really, the filtering process is a convolution and a time domain. So let us now flip back to today's presentation, and where to go? Okay, and so we've used these terms a little bit. I found a guy that explained this concept pretty well between the match filter receiver and a correlation receiver, and he starts with doing this comparison of correlation, cross correlation versus convolution. So you probably worked with convolution a lot in your previous courses, particularly in signals and systems, likely, and maybe even in some of your math courses. And we're used to working with that with particularly continuous deterministic signals, right? But when we're dealing with random variables, we're often interested in things like the cross correlation, or in the case, some cases, the autocorrelation, when we're looking at the same signal slid across itself, right? So these are very, very similar. So the cross correlation of two random variables, x of t and y of t, is you write it this way, right? So you write x of t, and then you write y of t minus tau, and then you look at the expected value of those two, right? And so over here we have this kind of tau parameter. Over here we've got a little tau parameter, right? So we have some t's spread around also, right? But let's not race to too many comparisons quite yet. Let me check our time. So okay, we got 2 minutes left in this recording, so in the Zoom session. So let's let tau equal to 0 right now. So now this term goes to 0, and we just have the expected value of x times y of t. And so that is if it's ergodic, right? So now we can calculate this expected value over time rather than having to pull an infinite number of samples from the potential set of random processes, right? So so instead of having to take many instances of these X and Y values, remember these are describing random processes, so they could take on different values depending upon the underlying process that describes its statistical properties, right? But if it's organic, we can kind of swap that for time. And so now we're going to calculate this expected value, and we do that by integrating from minus infinity to infinity, so we get that result, right? So cross correlation versus convolution. All right, let's fire up the other Zoom session and the other link, and I'll see you there in a couple of minutes.